Hello everyone. Welcome to this introduction to 2D dynamic programming. We will be focusing on how to solve problems on grids and matrices using dynamic programming. Let's get started by understanding the basic concepts. Let's explore the key concepts of 2D dynamic programming. First, problem characteristics. These problems typically involve traversing a grid or matrix. They exhibit optimal substructure, meaning the solution can be built from solutions to smaller subproblems. Also, they often have overlapping subproblems where calculations are repeated. Second, common applications. 2D dynamic programming is commonly used for finding unique paths through a grid, computing the minimum or maximum path sum, and navigating through grids with obstacles. Next, let's delve into state definition in 2D dynamic programming. In grid problems, the state typically represents the optimal value at a position given by I, j, where I and j are indices defining the row and column respectively. The value at dp of I, j can be derived using the function f, which depends on the values at dp of I minus 1, j and dp of I, j minus 1. This formula indicates that the current state depends on the states from the top and the left. Now let's look at a classic problem. The unique paths problem. Given an m by n grid, a robot starts at the top left corner, that is 0, 0, and tries to reach the bottom right corner. The robot can only move right or down at any point. The question is, how many unique paths are there to reach the destination? Here we have an example on a 3 by 3 grid with S indicating the start and E indicating the end. One possible path is shown with arrows. Let's explore the dynamic programming solution for the unique paths problem. To reach cell I, j, the robot must come from either the cell above, which is I minus 1, j, or the cell to the left, which is I, j minus 1. Therefore, the recurrence relation is dp of I, j equals dp of I minus 1, j plus dp of I, j minus 1. The base cases are the first row and the first column, for which there is only one way to reach each cell. Hence, dp of 0, j equals dp of I, 0 equals 1. Below is a Python code implementation that calculates the unique paths using this approach. Now let's walk through a worked example for the unique paths problem. Here is a dynamic programming table for a 3 by 4 grid. The cell at dp of 2, 2, which is at row 2 and column 2, contains the value 6. This value is derived from adding dp of 1, 2 and dp of 2, 1, which equals 3 plus 3, resulting in 6 unique paths to reach that cell. Now let's explore another problem, the minimum path sum problem. Given an m by n grid filled with non-negative numbers, the task is to find a path from the top left to the bottom right that minimizes the sum of all numbers along the path. The robot can only move right or down at any point. In the example, the grid is shown with one possible minimum path highlighted. The minimum path sum is 1 goes to 3 goes to 5 goes to 2 goes to 1, which equals 12. Let's look at the dynamic programming solution for the minimum path sum problem. To reach cell I, j with the minimum cost, take the minimum of coming from above, which is I minus 1, j, or coming from the left, which is I, j minus 1. The recurrence relation is dp of I, j equals grid of I, j, plus the minimum of dp of I minus 1, j and dp of I, j minus 1. For the base cases, the first row is the cumulative sum from the left, and the first column is the cumulative sum from the top. Below is the Python code implementation to find the minimum path sum using this approach. Let's walk through a worked example of the minimum path sum problem. Here are two grids. The first is the input grid and the second is the corresponding dynamic programming table. For example, dp of 1, 1, that is row 1 and column 1 equals grid of 1, 1 plus the minimum of dp of 0, 1 and dp of 1, 0, which equals 5 plus the minimum of 4, 2, which equals 5 plus 2, resulting in 7. The final minimum path sum from the top left to the bottom right is 10. To summarize, 2D dynamic programming problems typically involve grid traversal with optimal substructure. Common recurrence relation patterns include dp of I, j, equals a function of dp of I minus 1 comma j and dp of I comma j minus 1. Remember to initialize base cases for the first row and column. Also, consider space optimization techniques such as using rolling arrays to reduce O of m times n space complexity to O of the minimum of m comma n. Here are some practice problems to test your understanding. Unique paths with obstacles is a medium difficulty problem. Maximum path sum also medium. Dungeon game minimum HP and cherry pickup both are hard problems. That's all. Thank you. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.